The last recording in Chapter 7 is all about the regulation of pulmonary ventilation. So remember that ventilation is the liters per minute of air that we take in and out, and ventilation is determined by tidal volume and breathing frequency. And as with anything in the body, supply equals demand. So if the demand for ventilation goes up, the supply for that is going to go up to match that. So at rest, our ventilation rate is relatively low because we don't need to take in a lot of oxygen and we don't need to get rid of a lot of CO2. However, when you start to exercise, we've got an increased demand for oxygen and an increased need to get rid of CO2. So during exercise, ventilation increases. So what we're going to talk about here is the factors that affect the ventilation rate, and why does the ventilation rate go up during exercise? How does the body control that? So as you know, the control of breathing is involuntary, which means it is affected by the autonomic nervous system. Obviously, you can change your breathing rate voluntarily, but for the most part, you breathe without thinking about it and without intentionally breathing. So during exercise, when the need for ventilation increases, there are different things that cause ventilation to go up. Okay, so for one, the first thing that happens when you start to exercise is you get an SNS drive. You've got increased SNS action potentials going out, and this SNS drive, among other things, is going to cause an increase in ventilation rate. The second thing that kicks in is negative feedback, okay? Because when you exercise, if you exercise at low intensity, you need a little increase. Moderate intensity, you need a bigger increase. And higher intensity exercise, you need a greater increase in ventilation. And so the way the body matches the need for ventilation to the demand for ventilation is through negative feedback. And so the things that stimulate ventilation, there's various stimuli. For one, we've got joint movement. Okay? As soon as you start to move, the mechanoreceptors, the joint kinesthetic receptors in the joints that are moving, start sending signals to the brain, and this is going to affect the rate of breathing. And I'll show you that on another slide. There are various chemical factors that affect the breathing rate in addition. So when PCO2 starts to change, pH starts to change, and PO2 starts to change, these things can also cause an increase in ventilation, and these things are detected by chemoreceptors. And there are both peripheral and central chemoreceptors. The peripheral chemoreceptors are in the aortic arch and the common carotid artery, and the central chemoreceptors are located in the cerebrospinal fluid and the medulla oblongata. So specifically during exercise, the type of changes that are going to stimulate an increase in breathing, first of all, would be an increase in PCO2. Okay? And there's a star here because this is the primary effector of ventilation, or the primary regulator of ventilation. The other chemical stimuli that would cause an increase in ventilation would be a drop in pH. Okay? And we've talked about these themes throughout this chapter. And the greater the intensity of the exercise, the more your PCO2 is going to rise, the more your pH is going to drop. And so greater changes in these chemicals is going to cause a greater increase in breathing to match that increased need. Okay, remember that the peripheral chemoreceptors that are looking for these changes are in the aortic arch and the common carotid artery. Okay. The third thing that could affect breathing would be a drop in PO2. Okay. Theoretically, yes, if PO2 dropped in the aortic arch or the common carotid artery, this would be a problem. This would indicate a need for more ventilation, and it would cause an increase in ventilation. However, and the reason that I have this in parentheses is that PO2 rarely drops enough to have an effect, and we've talked about that, how the body is very good at resaturating our hemoglobin and keeping our PO2 levels on the arterial side fairly constant. So this is not going to happen very often, and probably not ever during exercise, because it's a very rare occurrence. The third stimuli for ventilation that would trigger a negative feedback response and help match the demand for air to the supply for air to the demand for air would be excessive lung stretch. Okay? And this would be something that would be detected by stretch receptors, and we'll talk more about those in another slide. So hopefully you start to realize here that we're talking about sensory motor integration and those typical steps that we follow, which is that there's a stimuli that's detected by a receptor. When the receptor is stimulated, it initiates an action potential that goes to an integrating center. Okay? And the integrating center for breathing is in the medulla oblongata and the pons, which are part of the brain stem. And the respiratory center contains two different areas. We have an inspiratory center and an expiratory center. The inspiratory center controls inspiration or inhaling. Expiratory center controls expiration or exhaling. Hopefully that's pretty obvious. Inspiratory center has intrinsic stimulation, okay, similar to what we see with the SA node. Okay. Just the way the SA node controls the basic rhythm of your heartbeat, the inspiratory center controls the basic rhythm of ventilation. So when the inspiratory center sends an action potential or initiates an action potential, it initiates an inhalation. The inspiratory center has this basic rhythm, but it also responds to changes, and those changes can come from the SNS. Okay, so when you start to exercise, you get more SNS action potentials at the intrinsic, at the inspiratory center, and this is going to increase the breathing rate. We've also got those mechanoreceptors feeding back about what's going on in the joints, and if the joints are moving, and the more they're moving, there's a greater need for inhalation, more frequent inhalation and deeper inhalation. And then the other three that we've already talked about would be an increase in PCO2, a drop in pH, or a drop in oxygen, which would be pretty rare. So the inspiratory center controls, it initiates an inhalation and also controls the amount of contraction force. Okay. So this would be helping determine the rate of breathing, which is frequency, and this would also help determine the degree that the inspiratory muscles contract, so the diaphragm and the external intercostals, and if there's a greater need for inhalation, the accessory muscles will come in, the sternocleidomastoids, scalenes, and pectorals, and this is going to help control the depth of breathing, how much air comes in with each breath. Okay. In the expiratory center, remember that expiration at rest is passive, so the expiratory center at rest is not active. Okay. Expiration at rest is just simply occurring because inhalation ends, the inspiratory muscles relax and recoil, and this automatically causes expiration. However, during exercise, there is a need to activate the expiratory muscles, and they are going to respond as a result of SNS. Okay, so the more action potentials that arrive at the respiratory center, the more likely the expiratory center is going to become active instead of passive. And the expiratory center also responds to excessive lung stretch. So the more you inhale, the more the lungs fill with air, and the more the lungs stretch. And the body has an upper limit for that. It's not going to let the lungs stretch forever. Okay, so you can imagine if you took too much air into a balloon, it would pop. So there needs to be a limit. So the body has this safety check so that if the lungs are inhaling too much, it's going to prevent them from prevent you from bringing any more air in. And the way you can stop inhalation is by stimulating exhalation, which ends the inhalation, relieves the stretch, and there you have your negative feedback. So the expiratory center is not active at rest. It can be active. It becomes activated during exercise, and what it does is it doesn't wait for inhalation to end. It cuts inhalation off and initiates an expiration. And it can also increase the rate of expiration, or it does increase the rate of expiration. So remember that normally expiration is passive. We simply wait for the inspiratory muscles to finish contracting for that equilibrium of that pressure gradient of air to occur. And once that occurs, the inspiratory muscles simply relax and recoil, and air goes out. However, during exercise, when the need for air is greater, we bring in the expiratory muscles, which are the internal intercostals and the abdominals. When the internal intercostals contract, they pull the rib cage down. So instead of waiting for those muscles to recoil, we pull the rib cage down, which decreases the volume in the lungs. And we also get the abdominals that contract, which push the diaphragm up, again, rapidly decreasing the volume of the lungs, increasing the pressure within the lungs, and forcing air to come out faster than it would have if it had been simply passive. So by bringing in the expiratory centers, we increase the rate of breathing, or the frequency, okay? Because the faster you exhale, the faster you can take your next inhalation. So by activating the expiratory center, this helps to increase the rate of breathing, okay? Okay. So the inspiratory center, changes in the inspiratory center are going to increase the frequency of breathing. And changes in the expiratory center are going to increase the rate of breathing. Changes in the inspiratory center is going to increase the volume of air that comes in, and together that will increase the breathing rate through negative feedback, matching the supply for air to the increased demand for air. Alright, so just putting this all together in a figure from your book, we've got sensory motor integration, right? We've got a stimulus, we've got receptors that detect that stimulus, okay? We have an integrating center, that sends out information about responses. And then we have the final effect, which helps maintain essentially homeostasis, matching supply and demand and the need for whatever's going on at that period in time. So now we've got this occurring in the two centers. So we've got stimuli arriving at the inspiratory, stimuli information arriving at the inspiratory center, and we have stimuli information arriving at the expiratory center, and we have responses coming out of the inspiratory center and responses coming out of the expiratory center. So again, I'm just repeating myself for what we've already talked about. So if you get a stimulus Some of the stimuli include an increase in PCO2, a decrease in pH, a decrease in PO2, and also signals from the active muscles, and those are the mechanical receptors, sending information to the inspiratory center about what's going on. And if there's an indication that PCO2 is up, pH is down, PO2 is down, mechanoreceptors are activated because muscles are moving, the inspiratory center, the integrating center, is going to interpret this information and determine a response. And in order to increase inspiration, the response is going to be that the external intercostals and the diaphragm are going to contract to a greater degree, and possibly, if the need is great enough, those accessory muscles are also going to be activated, the sternocleidomastoid, the scalenes, the pectorals, and they're going to send information to those muscles to increase breathing, increase the degree of contraction, which is going to increase in volume of the lungs, which is going to decrease the pressure in the lungs, which will draw more air in. The expiration center, when it is activated, it's activated partly by SNS, but also from the stretching of the lungs. Okay, so I said that if the lungs stretch to a threshold degree, the body is going to initiate expiration to prevent further inspiration, to prevent over inhalation or overstretching of the lungs. Okay. And this is called the Herring-Brewer reflex. Okay. And the response of the expiratory center, if it's stimulated, the response is going to be that the expiratory muscles become activated, and we've got the internal intercostals and the abdominal muscles, which are going to cause thoracic volume and therefore lung volume to decrease rapidly, which is going to increase the pressure inside the alveoli rapidly, setting up a pressure gradient that's going to force air out. Okay, so sensory motor integration, it's all based on negative feedback, and the reason for that is because negative feedback helps the body to precisely change what is needed to change in order to maintain essentially homeostasis. So the greater the increase in PCO2, the greater demand there is to get rid of CO2, and the greater the response is going to be. Okay, and that response is matched because the integrating center receives information from those receptors about what's going on. The inspiratory center interprets that information, and from that it knows how much, for instance, PCO2 has gone up. If it's gone up a lot, then the response needs to be greater. Okay, and so the response is going to match the stimulus through negative feedback, and therefore the body is going to precisely control breathing depending on the needs. So when you exercise with a little intensity, you're going to get a little bit of an increase in ventilation, and when you exercise with great intensity, you're going to get a greater increase. And the reason why you're getting a greater increase is because of this precise negative feedback mechanism that is occurring between the receptors, the integrating center, and the stimulus and response, and the response that's sent out. Okay, so pretty logical, makes a lot of sense. Similar theme that we've seen throughout all the body systems is that control is essentially controlled by negative feedback, so that the response matches the need, and not more and not less.